All right, we're going to look at the difference between, we're going to look at inelastic collisions now. So specifically those inelastic ones. Again, the difference between elastic and inelastic, the, the extreme, so 100% elastic versus 100% inelastic. One way we see elastic collisions is that they hit and they bounce off. And inelastic, they stick together. Now, for both of these, momentum is conserved. And so momentum before equals momentum after. Now, let's look specifically at inelastic. So let's start with a drawing of what happens here. So 3 parts of a collision. We have before, we have the collision itself, and then we have after. So let's go with red and blue. So here's a red object, and it is moving in this direction. And this time, let's have a blue object that is sitting still. So not moving, no arrows. Then they collide, which means that the red will then hit the blue. And then after they hit, the red and the blue stay together. So there's red, and then here's blue. And as they move together, they will be going slower than the red was initially. It's that whole conservation of momentum. Now, what causes all of this to happen? Well, the red one is initially going fairly fast, and then now it's going slow. And so that is a change in momentum. Speeding up and slowing down are both ways to change momentum. The blue one is going from not moving, right here, to moving. That is also a change in momentum. Change in momentum is impulse. So that means at the point of collision, an impulse is happening. Impulse means a force is applied. Now, the red one applies a force to the blue, and that's what causes it to start to move. The blue applies a force back, which causes the red to slow down. Now, based on Newton's third law, we know that those forces are equal. And since the forces are equal, the impulse is equal, which means they have the same change in momentum. That is why momentum is conserved in inelastic collisions as well. Now, for the math, we have m times v equals p, so mvp, and then we have m times v equals p again. Now, the difference is for the after. So this is the collision. Collision. Here we go. There we go. All right. So with this collision, object 1 and object 2 are now staying together. And since they are together, they will have one momentum. Since they're staying together, they will be going one velocity, the same velocity, since they're together. So it kind of makes the math a little bit simpler than elastic collisions. So let's do an example. No, MVP, MVP. So here's car 1. The first car is 3,000 kilograms. It is going 50 meters per second. The second car, it says rear ends another car. That one is 2,000. So car 2 is 2,000. And it is also moving at 35 meters per second. Here's our key phrase. If the bumpers of the cars become attached, that's how we know it's inelastic. They stay together. That means automatically we have one velocity and one momentum. So it's not two separate numbers anymore. It's one number. So with that, let's do some math. M times V equals, let's see, 150,000. And then blue is 2,000 times 35, which gives us 70,000. All right, let's see. Our masses are going to stay the same. So we got 2,000 here. And we got 3,000 here. That whole conservation momentum thing. So momentum before equals momentum after. So let's see. What is our total momentum? Let's see. We've got, looks like 220,000 here, which means that our total over on the right is also going to be 220,000. Well, here's what's kind of cool. Since they're together in the end, they have one momentum. And so that's why I drew that box. And so inside the box will be 220,000. Let's see. Okay, they're going to have the same velocity too. Well, I guess if they're together, then that means the masses will be together. And so the total mass is going to go a certain velocity and have a certain momentum. Now we can find the V. So 5,000 times V is 220,000. And we divide by 5,000. Get V by itself. And we get an answer. Oh, let me erase my box. There we go. So we get an answer of 44 meters per second. Now, because of conservation of momentum, the velocity of the two together should be between our two initial values. So car 1 was going 50, car 2 was going 35, and sure enough, 44 is in between. It's a way that you can check your work. Make sure that you're getting the right answer. All right, let's try another example. Make sure that we're good. Let's see. Start with MVP, MV, and P. Okay. 2 cars again. So we got car 1, and we have car 2. Let's see what's going on. 1,000 kilogram car. All right, so that goes right here. Hits a 2,000 kilogram car at rest. All right, well, that's our other vehicle, isn't it? So 2,000 kilogram car at rest. Now, rest means not moving or 0. The 1,000 kilogram car, all right, well, that's our red one, isn't it? So the 1,000 kilogram car has an initial velocity of 40. So that goes here. If both cars become entangled, oh, all right, there's our keyword. Now, if you don't know what that word means, if you think about when your hair gets tangled, then it all gets kind of mushed together, right? It gets knotted up. And so entangled is the same idea. They then become 2 objects that get twisted together. And so this is again meaning together. So that means 1 velocity and 1 momentum. All right, we're looking for final velocity. Well, let's go ahead and get started. M times V, so that would be 40,000. 2,000 times 0 is 0. All right, so our total is 40,000. Now let's go over here. Well, we know total momentum before equals total momentum after. And so 40,000 will go right here because it's together. Let's see. Masses are going to stay the same. So we got 1,000 and 2,000. Since those are also together, they should add together. And so we can now solve for our V. So we have 3,000 times V equals 40,000. To get V by itself, we divide by 3,000. And we get 13.3 meters per second. Now, using our rule of thumb here, making sure our number is reasonable, our initial velocities here were 40 and 0, and we got 13.3, which is indeed in between those two. So that seems like a reasonable answer. All right, well, that is it for inelastic collisions. If you would like to see a different method for how to solve these, one that does not use this chart style method, but instead uses an equation, specifically on the equation sheet for inelastic collisions, make sure you go back and look at the 2020 Heier video. on collisions, or the one that says old collisions. Both of those use the old style with the inelastic collision equation.